with Nicholas's contact information. I'll do that this evening, so that'll appear in the class Dropbox. But what I'd like to ask you to do is, since Nicholas is here with us, I won't be monitoring the chat as much, so I have sort of been keeping an eye on it in the last couple classes. This class I won't so much. So if you have a question, Nick will sort of give a first pass at it. If he's able to answer it, great. If he isn't, there's some things that of course are very specific to the lecture I'm giving at the moment. Just raise your hand at that point, and then that'll catch my attention because it gives me a little notification. Outside of that, Nick will be available to answer technical questions via email. But also, of course, still feel free to email me. So, Nick, I look forward to having you on the team, and I think it'll just make this course all the richer. So, we all appreciate you being here. So, what I'm going to do is I'm going to share my screen with everyone, of course. Great. So you can all see my screen, just double checking.
Yep.
Great, excellent. So what we're going to do is we're going to pick up from where we left off last class, and we're going to sort of look at two topics this class. So the first topic we're going to look at is we're going to kind of review how I went about creating these sidewalk outlines, because I did sort of breeze over in the midpoint of last lecture, which maybe isn't the most logical place for that little sub lesson to go. So we'll quickly go over that. I'll go into how you will go about splitting your draped surface. So at the end of last class, we ended up with this draped surface, and how you can sort of express the difference between sites, sidewalks, and roads. Following that, what we're going to do is we're going to explore the use of blocks in Grasshopper and Rhino. And we're going to use this to analyze the tree data that we got from the city of Vancouver in order to populate this little section of the city with the trees. So what I want to point out is that if you look in the Dropbox, what I've done, just so we're all on the same page here, you can go ahead with your own site file, of course, but if you do want to follow exactly what I'm doing, and focus on this site file here, I've saved in the lecture files under today's date, so 06/22 site model finale. Even if you're working with your own site, we will be working with some blocks, and so you can quickly reference those. Those will be in this folder trees 2D, and this just contains two Rhino files, so I can quickly open one right here, but all they are kind of simple SketchUp style cutout trees like that. So there's just two of them. So if you want to use those with your own file, perhaps download them right now. The other thing in here is the street trees, City of Vancouver Open Data Portal entry. So we're going to return to this. Again, if you remember in our first class when we are accessing all the City of Vancouver Open Data Portal, essentially we just downloaded the street trees data. So I've just saved it here for our convenience. You might already have that downloaded if you've been following along. All of this, of course, it's kind of the final two steps of finishing up assignment 1. So we're going to start out with splitting some sidewalks. So I'm just going to bring this up. Okay. All right. So essentially what we're going to be doing is we're going to be taking the 2D information that we've traced from our ortho image, and I'll quickly review how we did that, and then we'll be splitting the ground here. So what I want to do right now is go into the layers if you're using this file. If you're using your own files, your layers should be organized in a similar manner. And what we're going to do is we're just going to, maybe I'll just switch to the default layer here. I'll turn off the 3D information. I also have this draped ground layer. I'll turn that off as well. And I'm going to go to this layer here that I have called drawn sidewalks. And if you remember last class, we made a layer called drawn sidewalks. And what I did was I just very quickly went over how I traced the outline of this sidewalk right here. Just to review, I'll trace one more sidewalk just so we're all on the same page. So very simply, the best way to do this is just to offset your lot lines. So let's go offset. The distance, you can essentially just look at your image and figure out roughly the distance you want to offset. So in this case, I can just click on distance, and I can just snap from this point right here to approximately that point right there. And you can see what's going on is that I am roughly tracing the sidewalk on this edge right here. It looks like it comes in a little bit, but that's fine. What we can do here is we can essentially just draw, a line. This is very just simple 2D drawing. So I'm sure a lot of this is review for you, but I just want to go through it so it's not sort of lost in the mix. Here's another side, and then what I might do is just do the same thing here. I see the edge right there. And now, more or less it looks like we've traced roughly the edges of this sidewalk. The tool that I really like using that I've mentioned before is the curve boolean. So you can click the drop-down menu on your curve tool here. So that's the fillet curves button. If you click the little blue rectangle in the lower right-hand corner, essentially you can click the little square intersecting with a circle, and this will be curve boolean. So you can click that. You can see a little dialog box comes up. The one that we really want to change from default is this delete input. We want to change it from delete input equals none. If we click it, we can go delete input equals all. And that's just going to get rid of any of these curves that we're not using, and it'll just give us the remainder, the intersected area. Combine regions equals yes, output equals curves, and then all regions we can just leave like it is by default. Click inside the region you want to keep, and then you'll just get the darker black lines showing you the region that will remain. So once you're happy with that, you can adjust this region by clicking different areas, but once you're happy with this region, just click enter and it will give you the region that you want to remain. From here we can just fillet our corners. So we can click this same button here, fillet curves. You can also type fillet. And the radius, I think, was 9 meters. Again, you can try a few different things. So that looks good at 9 there. I'm gonna, fillet these 9 meters as well. And, I'm gonna say that's done. For the sake of this lesson, I think that's close enough. Now, for your own site model, if you're working, a project for studio or whatnot, you'll probably have more exacting information about the edge of the sidewalk. But, for our sake in this class, this is good enough. So, now we have these curves. So these are all the sidewalk outlines. What we're going to do is we're going to turn back on our layer draped ground. So if you remember, we had a I'll just turn on here. This is the ground mesh, which we imported from Cloud Compare, right? So this is from the LiDAR data, and what we did was we used the command drape to essentially drape this surface over that mesh. Further to that, we took the shoreline two-dimensional layer that we imported from the City of Vancouver Open Data Portal, and we used that to trim the coast. So that gives us a fairly accurate shoreline. So what we're going to do now is we're going to split this surface just with the sidewalk outlines and the site outlines. What we want to do is we want to make a new main layer. So what we can do is we can go new layer. We can just call it ground. And we can make a few sublayers in this main layer. So we can right click ground, go new sublayer, call this first one GHREF untrimmed. So what I mean by GHREF untrimmed is we'll want to reference this surface just as it is. So technically it is trimmed because we've trimmed the shoreline, but we don't want any more trim than this. We don't want it split. So maybe a better thing to call it is unsplit. So maybe I'll change it to unsplit. But essentially we want a version of this that we can reference in Grasshopper that we don't modify. So what I'm going to do is I'm going to select my draped ground surface layer right there, right click GHREF unsplit, and then go change object layer. Now I can just delete this draped ground layer. So now the GHREF unsplit layer is just our draped surface. I want to make a few other layers, so I'll just right click on the GHREF unsplit, or I could right click on ground, go new sublayer, and then I'm going to call this one road. I'll make another new sublayer, so new sublayer. I'll call it sidewalk, and I'll make a new sublayer. I'll call it lot. So essentially we're going to have the roads, the sidewalks, and then the building lots themselves. And now we simply just split. So what we can do is we can take this drape surface. I just selected there, and maybe I'll select my road layer. I'll right click the road layer and go copy object to layer. And now what you can see is that we have two of these drape surfaces. So if we turn off our Grasshopper Ref unsplit layer, we'll still see this same surface there because it's now also on the road layer. If we want to differentiate this through colors, I personally like using colors to sort of visually differentiate my layers. We can just click on the little black box there and change its layer to maybe a dark gray asphalt type color. So I'll click OK. So there's our road layer. So now what we're going to do is we're just going to split it. So why don't we split this road layer with all of our sidewalk curves? So if you're working along in your own file, you should have some sidewalk curves, or at least you'll have a few of them. If you're working along in the file I provide in the Dropbox, you can just select the layer Drawn Sidewalks. So I'll right click this layer and go Select Objects. And you can see it's just selected these 2D layers. Simply what we're going to do is we're going to extrude them. So you can go Surface, Extrude Curve Straight. Or if you want to, you can type Extrude Curve. They both do the same thing. And essentially what you're going to want to do is, for splits like this, usually I have both sides on, and just make sure that you're extruding straight up. If you're not extruding straight up, what you can do is click on the direction option, go into one of your front or right views, and hold Shift to snap into ortho mode, or click the ortho mode button down here and just drag straight up. So click once, drag straight up, and that'll set the direction to be straight up. So now I'll just drag these surfaces up like so. I'm not going to delete these 2D drawn sidewalk layers. Maybe I'll just leave them as such, just for, you know, future plans. And then what I'm going to do is I'm going to select the road layer. So I can just select this object here. I'll click the split button, so not trim, but split. So a little triangle splitting this rectangle, or else, of course, we can just type split. And then, so with the object we want split selected, we select that option. Then we're prompted to select cutting objects. We can select all these extrusions we just extruded. So I'll select all those, press enter when done. I'll press enter. And now you can see we've split these surfaces. So what I'll do now is I'll just deselect this area that we've split out. So what will be the road? And as I'm seeing this, I realize we need to split out a beach layer or a park layer as well, but just deselect everything that's not within the lots, and we can just change those to the sidewalk layer. So I just deselected the road layer, and now all the remainders, I'll right click on the sidewalk layer and go change object layer. And now we can sort of see a differentiation. Now you can see here that a few of these layers didn't split. That's fine. We can quickly fix that. So what we can do with this is we can just modify these 2D sidewalk curve layers. So I'm going to delete all of these extrusions. So I'll just go into sort of a side view and perspective, select all the extrusions, click delete. And then what I'm going to do is I'm going to go into my top view and fix the curve intersections that didn't intersect fully. So let's double click on perspective, go into the top view. Let's go to wireframe. So go to view wireframe, or you can click on the drop down menu in the top left of the screen. So go to wireframe. And then what we want to do is we just want to extend any curve that's not intersecting with the edge of this surface. So you can see this wasn't split because this sidewalk edge didn't intersect at this point. So what we can do is we can just use the command extend. So you can either type extend like so. Just click. So you can type extend. Select the boundary objects or enter extension length. Press enter for dynamic extend. So we can just use dynamic extend. So you can press enter. And what you do then is you just click the end of the line you want to extend and extend it. So I'm just clicking these lines and extending them so they fully go off the edge of this surface there. So that's the edge we're aiming for, this gray one right here. So again, another way of doing it is going to curve, extend curve by line, and then in this case, dynamic extend is already enabled, so you can just click the ends of the curves you want to extend and extend them. So what I'm going to do now is I'm going to select these curves, and then again I'll just go into kind of a side view but in perspective, and then I'll again go surface extrude curve straight. Again, you can type extrude curve and then select the object we want to split. So it's this remaining road layer. Click the split button or type split, and then select the objects that you want to split this road layer with. So that looks like it worked. I'm going to deselect that road layer. The remaining sections here are still selected, so I'll right click on the sidewalk layer and go change object layer. These extrusions, I'll select them, I'll delete them, and now you can see we're starting to get a nice outline of the sidewalk blocks. So what I'm going to do is I'm going to create a new layer under ground. So under the ground parent layer, I'll just right click this, I'll go new sublayer, and then here I will just go to beach. Could be named park, whatnot. And what I'm going to do is I'm just going to separate the road from the beach. So let's go into top mode, and it looks like this lot line that I have here works quite well for that purpose. What I'm going to do, since I'm on the drawn sidewalks layer, maybe I'll just trace this property line that we imported from the City of Vancouver Open Data Portal. So I'll just select the polyline tool, or I could also type polyline, and I will just sort of select the vertices of this line we imported in from the City of Vancouver. So I'm just kind of tracing it. And the reason why I'm tracing it and not just using it is just because I want to make sure we have this data sort of brought in from the City of Vancouver being its own thing that we can always refer back to, so it's the original record. From here, you know, we could edit this curve so you could see that the sidewalk does indeed extend beyond the actual lot line. You could also fill at the edges. You know, I'm not gonna really bother right now, but for your own site model, if you want to do that, you can. Make sure the lines extend past the edge of our road surface, and we're just going to do the same thing. So we'll just go into the perspective mode, and we will just go surface, extrude curve, straight. So we get this big surface. I can see already that I've made a mistake right there. This doesn't intersect, so it's not going to split. So what I'll do is I'll just drag this point and just drag it out like that. So make sure it lines up. So now I have this line here. I can do the same thing. I'm just going to go to surface, extrude curve, straight, like so. I'll select the surface I want to split. I'll select the cutting object, delete the cutting object because I don't need it. Now I have the beach here, so I'll right click this portion of the surface. I'll right click where it says beach right here and go change object layer, and then I can even, you know, change this to a sandy color to indicate a beach. So that is essentially our beach layer right there. So the final thing we want to do essentially is we want to split the sidewalk layers. We want to separate out the actual legal lots from the sidewalks. So that's very important because that's going to be, you know, the basis of your site coverage calculation, later your FSR calculation, and also for rendering purposes, you probably want your building to interact with the public, and that's what sidewalks do. So what we're going to do is we're going to select the block outlines layer on our 2D info parent layer. This is essentially the layer that we just brought in the lot lines from the City of Vancouver. We'll just go select objects. We can deselect, you know, these lot lines that are on the beach because we won't really need them. Furthermore, I guess I forgot a park right there. So that looks about right. What we'll have to do though is we'll have to extend these lines as well. So I'm realizing we need to extend these lines, so that's easy enough. So what we'll do is we'll just type extend curve, or it's just extend. We'll hit enter for the dynamic extend, and then we'll just extend these lot lines like so. Okay, we're just making sure that these lines intersect with the edge of the surface here. And now what we can do is we can go back into perspective. We can right click the block outlines layer, go select objects. Again, we'll deselect the lot lines that are on the beach, and then we'll just extrude these up. So we'll go surface, extrude curve, straight. So that looks good. And now by this point, this is all sort of habit. We'll just select the, actually what we can do is we can just select the sidewalk layer, probably the easiest way to get these objects. So we can go to our sidewalk layer, right click it, go select objects. So all those objects there are selected, sort of zoom back into more of an elevational view, and then click the split button or type split, and then go select cutting objects. We can select these extrusions. So I'll hit enter, and then it'll take a moment to split. So you can see there is split. What I'll do now is I'll delete these extrusions. You can see those surfaces split, exactly how we want them to. So what we're going to do now is we're just going to select the centers of those surfaces that we just split, like so. And now we can change these layers to lot. So I'll right click on the lot layer, go change object layer. I'll change its color just so we can visualize that a little bit better. But now we've differentiated between the actual lot lines in the sidewalk. Now, the only thing I want to do, and this is mostly for a visualization purpose, but however, it is, I think, a useful thing to do, and in all the site models I've made, I've always done this. It just adds a little bit more depth, and it's also useful for things like shadow calculations. Essentially, we want to raise this curb off the ground, so sidewalks have curbs. And I mean, it's not exact to the LiDAR data, but neither is this. It's a draped surface, so I feel confident that we can select our road layer, our beach layer, and then what I'm going to do is I'm going to move this down by 6 inches, and that'll give us our curb all around here. So if you don't have Gumball on, turn on, excuse me, turn on Gumball. So it's just right down at the bottom of your screen. And then you can click on the blue arrow. So this means move in the Z direction. And then I'll just type -6 inches. So -inch and then the quotation mark. So -6 inches, enter. And you can see that all of this has been moved down by 6 inches. Now what we can do is simply we can grab all the edges of these surfaces here, and maybe we should have done this before we split these surfaces now that I think about it, but it's okay. So the easiest way to grab edges is simply just to go, maybe we'll grab the edges from the road actually. So what I'm going to do is I'll show you a layer that I find very useful for working on things like this. Is we're going to type isolate. And I believe that's under edit, edit, select objects. To be honest, I don't actually know where it is. I always just type isolate. So essentially, just type isolate. And this essentially is going to isolate the thing that you have selected. So I had the road selected right there. And then I'm just going to type isolate. You'll see that our ortho image layer, because I've locked in this file, it didn't disappear. If we also want to get rid of that, we can just type or hold Control-Shift-L. So that's the shortcut for unlock. We can select this ortho image as the object we want to unlock, hit enter. And then now if we were to run the isolate command again, so I'll just type isolate, it would just isolate our road surface here. So what we're going to do now is why don't we set our layer to sidewalk. So we can just click next to the light bulb on our sidewalk layer, and the check mark of course means it's the current layer. And then what we're going to do is we're just going to go to curve from objects, and then we will go to duplicate border. So duplicate border, and then we'll select this surface. I'll hit enter, and you can see this gives us all the edges of the road. Yeah, if you're unable to isolate, the other thing you can always do is just, like, let's say we have all this stuff here. Sort of the long way to do is exactly what Oliver was saying. So you can just go edit, select objects, invert, or else I believe you can just go, or what you can probably even faster than that is just Control A to select all objects. Hold Control to deselect the road surface or whatever you want to isolate, and then just type hide, and then that'll do the same thing. So from there, I'm just going to go over the curve command again. So we're going to go curve from objects, and then we'll go duplicate border, and that just gives us the edges of this surface. What I'm going to do now is, because we only want these borders around our sidewalk edges, I'm just going to hit the explode button, or you could type explode. And essentially it's going to explode all this. Now before we sort of deselect it, I'm just going to deselect the edges here. So all I'm doing is I'm selecting essentially the edges that we don't want that are sort of joining the edges that we do want together. So I'm just deselecting these kind of attachment pieces, as it were. So I'm just holding Control right now, and I'm clicking on the pieces I don't want. That's deselecting it. You can also Control drag from the upper left-hand corner like that. And we don't really have to care about this edge. Like, we don't have to deselect all of this, because what we can do is we can just deselect the joining pieces. So now all those joining pieces are deselected. We'll now click join, or you can type join. We can deselect, or we can just select all the curves. So I'm just selecting everything here. And then we can essentially just deselect the things we don't want to delete, which are the edges of our sidewalk. So essentially the only things left selected are the edges we don't want. Now, if we have all of our curves selected, so I'm just going to select everything and then deselect the road. In this view, you could also go edit, select objects, curves. So once you have those edges selected, since we're on the sidewalk layer right here, we can simply go to surface, extrude curve straight, or you could type extrude curve. Make sure both sides is off. So you can see right now it's extruding in both directions, so both sides equals no. Direction for me looks fine, but again, you can click direction, go into your side view, drag straight up if you need to correct that. Drag above, so you're in the right direction, so drag up a bit and then type 6 inches. So 6 and then quotation marks, enter. And now just confirm that your curve did indeed extrude upwards. And now you can see you have your curves. What we can do now is I will hold Control Shift H, and that's to unhide objects. And then what I'll do for right now is I'll just right click on the sidewalk layer, go select objects. So I'm just selecting the sidewalk layer. I'll click enter to unhide all those sidewalks. I have a curve there I can delete. And then what I can do is just right click the sidewalk layer again, select objects. So I'm selecting all the sidewalk surfaces as well as their curbs. And then I'll just hit join. I can also type join. So now if I hit Control Shift H again, select everything, you can see what I have is a nice kind of uniform curve. Now this is of course a little bit of an abstraction. This curve, varies a little bit in real life, but especially in a model like this, it instantly gives you the ability to see where we're dealing with road and where we're dealing with sidewalk. So this is, to me, the level of finish I'm looking for in that differentiation of layers in your assignment 1. So does anyone have any questions about that? Or about any of this sort of Rhino-based site model stuff? Okay, so that's perfect then. So what we're going to do then is I am going to essentially just turn off a few layers here. So I will turn off the ortho image. I will turn off, I guess, all the 2D info. I'll turn off the drawn sidewalks layer. And essentially what you see here, of course, by the 4x6 extent, plus the trees we're about to put them all, this is about the level of completion I want for your assignment 1. So this gives you an idea of what I'm looking for. So what we're going to do now is we're going to insert some trees into this model, and we're going to review, because I think that if we go back to a grasshopper definition that we sort of worked on a week ago from today, it might be a little bit hard to pick up from where we left off. So we're just going to start from the beginning, sort of make a new definition for the trees as a little bit of a review, but then we're going to dive into some really interesting topics. One thing I wanted to mention is, again, last night I sent out the email asking you to download the plugin Instance Manager instead of Elefront. Sorry, I made a change to the syllabus and forgot to update the syllabus. So for this, please make sure that you have the plugin Instance Manager installed. What I can do right now is I can just copy it to the Dropbox, so you can grab that. So I'm just going to go to my components folder and then grab the Instance Manager plugin. Copy. And I will put that in today's lecture file if you need it. Okay, that should be there. There it is. One thing I want to bring up before we get into trees as well, actually I just have in my notes here and I want to mention it, is Lydia got in touch with me over the weekend because she discovered a little bit of a bug. And essentially what the bug was that Rhino cannot import images of a certain size. So in the case of importing the ortho imagery, 300 megabytes-ish didn't work, 120 megabytes did work. So the way that you can sort of rectify that situation if it happens to you is export from GeoViewer, the highest resolution, and then essentially have its size in Photoshop. And that'll still give you a high enough resolution image to trace, but it will not give you that error. So I just wanted to point that out. So we are going to essentially work with blocks. So I'm going to show you what a block is. So if you go to the Dropbox folder, like I said, go to the lecture files, today's date, and then trees 2D. Essentially, here are two blocks. So let's open tree 01. So all I've done here is I've just made a Rhino file. I've made sure that its units are meters, because our other files, our main files units are meters. And rather than that, this can just be sort of anything you want. Like, it doesn't have to be a tree, it can be a car, etc., etc. A block is essentially just an instance of something in a file. So we'll look into that a bit more. And the way you can bring this in is essentially you can go to File, and then you can go to Insert. So Insert is different than Import. Import will sort of just, in a dumb matter, bring in the tree. So we could go to Import. We could bring in tree01. And then what happens is if we looked all the way at the origin, so we'd just have this tree there. And it has all the same features that were given to it in the tree01 file, but there's nothing really special about it. It's just brought into this file. So instead of doing import, we can always go File, Insert. And now we get this little bit of a different prompt here. So the first thing you'll notice in this insert, option dialog box is the name with the little folder there. So you can click the little folder, and this will essentially allow you to browse for whatever file you want. So in this case, we can go into our lecture files, our site model finale folder, trees 2D, and then we can choose tree01 10 meters tall. Open. And now it's going to give you some options here. So the first one is you can give it a name. So the name of the file is tree01 10 meters tall, and it'll be given that name by default. You can always change it at this point. So for example, you could just simplify it to tree01. Using Rhino 5 and can't open the tree files. Okay. Why don't I quickly save them?
I can do that if you want.
Yeah, that'd be excellent. If you just resave them as Rhino 5, that'd be great. Thanks, Nick. So essentially, we're going to, again, just import the tree01. I'm going to name it to tree01. And then essentially, it's going to give you this prompt. So the second one, external file, read link blocks from the file. I usually have this unclicked because if you're sort of importing blocks of blocks, things can get messy. Sometimes you might want to read blocks if you're importing, let's say, an AutoCAD file. So there's a few different block definition types. Embedded means essentially it's going to create a block, which we'll go into a little bit more what that means. And it's going to live in this file. So in other words, if you modify the original Rhino file, it won't change in this file. And essentially cannot choose the Rhino file in insert. Is it a Rhino 5 as well? I'll just see if you guys can figure that out. So anyways, embed just means that it is embedded in this file. Embedded in linked means that it is embedded in this file. If the link location, let's say we deleted tree01 from the Dropbox file, it would still exist in this file. It just would no longer have that link. And then linked means that essentially it is linking to this Rhino file, and if we update this Rhino file, it will update. If we delete the Rhino file, the block will disappear from this file once we update it. So a lot of the times when you're working in Office, you'll use linked just to keep your files up to date with the most current, let's say, AutoCAD sets. However, for this course, we'll use embedded, just because we don't want to deal with sort of having this big web of files relying on other files. So I'll encourage you all to use embedded. So we'll just choose embedded, click OK. From here, you can write a description if you really want. And now you can, you don't have to insert it as a block. You can insert it as, let's say, a group or individual objects, but we'll work with blocks. Insertion point will prompt. Scale will be uniform. rotation we'll just leave 0. So we'll click OK. And now you see, since we prompted for the insertion point, instead of going to 0, 0, 0, it's going to a position that we choose. So I'll just place this over in the beach, so maybe on the edge of the beach right there. So we have this little tree on the beach. So the question is, why would we use a block? So what I want you to do is just to select tree 1, and then let's just go transform copy. Now there's 2 of these. What we can do is, you can see when I select this object here, it says 1 block instance add to selected, or to selection. It's sort of a group right now, right? It's not an individual object. But what you can do is you can double click it, and that's essentially going to bring up the mode, block edit mode. You can also, if you really want to, type block edit. And essentially what we can do in here now is if we edit this object, so let's just say, for sake of demonstration, I'll stretch this out. I'll click OK. Now all of these will be stretched out. So this is going to be really useful for something like positioning the trees, because you could always imagine you can use these simple 2D images as sort of placeholders for the trees. But once you're ready to sort of maybe render out your file, let's say, you could always double click on this and then, you know, put in a different tree or a more complex tree. Or let's say you want to do a winter render, all of a sudden you change it to a Christmas tree, right? So you just click OK, and now all your trees are now Christmas trees. So this is why we use blocks. If we think forward to what we're going to do later on in this course, so stack up towers with voxels and then create units that sort of fit within those grids of voxels, you can see where we can start to use blocks very effectively. So you will be able to, for instance, change an apartment unit. You can just swap in different units in and out. So that's sort of a basis to a primary topic in this course and using them in Grasshopper. So now that we have that kind of established, does anyone have any questions about blocks? Okay, so what I'll do is I'll just I'll bring in the other tree. So I brought in tree 1, so this will be a little review. We'll go to File and then Insert. I'll select tree 2. Thanks, Nicholas, for the Rhino 5 files. So I'll select tree 2, click Open. I'll call it tree02. You can leave it the same. It'll be an embedded block. I'll click OK. Insert as block instance. Insertion point prompt. Scale uniform, so 1. And then rotation 0. And we can just place it next to our other tree. So there are our 2 trees. So what we're going to do is we're going to jump into Grasshopper, and this will be kind of our first, I'm going to say, more in-depth tutorial in Grasshopper. So we're going to use Grasshopper quite extensively in this class, and we're going to use it to distribute the trees throughout the city based on the City of Vancouver Open Data file. And we're going to do so just for our sort of site model right here, or yours might be a little bit different. So what I'm going to do is I'm going to open Grasshopper. So typing Grasshopper, you can click the little Grasshopper button right there. And we're just going to start afresh, a new file. Make sure that you have Instance Manager. Again, it's going to show up under hetero, I guess it's hetero Heteroptera. I'm assuming Heteroptera. Maybe the P is silent, but it's going to show up under this name here, and you'll just see that there will be the one tab called Instance Manager. And you'll also see some new primitive types, so the block instance and block definition. So I'm just going to open my notes. You can start from a blank canvas. Jeremy, so what you might need to do, so if it is not showing up, what you might need to do is open your special components folder, so file, special folders, components, and then just right click Instance Manager, properties, and then click unblock if that's the case, and then restart Grasshopper. Now if it's still not working, you might want to go to Food for Rhino. I'm just bringing it up on my other screen. And download a different version of Instance Manager. Although this one should work because it says it works for Windows 4 and 5, Windows 6, and Mac 5. So I'm sure it's just blocked. Okay, so I'm just going to open my notes here. Let's see. Okay, so this is sort of a preview of what we're going to do. Just let me review for 1 second so I remember what it is we're doing. Okay, so we're going to start off with a little bit of review. So essentially we're going to use the @it plugin that we used before. And we're going to bring in the tree information. Like I said, we did do this kind of in a very rudimentary fashion in class 1, but we're going to go over that again. I think that's just going to be easier than trying to salvage the first class sort of beginning of a Grasshopper definition. So let's just start from scratch. Again, the shapefile that I'm going to be using is also in the Dropbox folder under the Street Trees folder. So if you do need that, you can use this. So what we're going to do is we'll click @it. So again, it's this plugin that allows us to bring in shape files. And we'll click on the shape tab, and then we'll go to imp @it. So import @it. So imp @it has 3 inputs. So the first one's the shapefile path. The second one is project to WGS84. Remember, we are in the EPSG 9610, I believe, projection, the EPSG anyways. So that more local, smaller scale projection. So this will be false. And then a true or false Boolean toggle to just sort of start this component. So the only thing we really need that's sort of like unique information is the shapefile path. So let's define this. So let's go to params, and then we'll go to primitive, and then we'll go to file path. Now, once you've selected params, primitive, file path, we can right click that parameter and go select one existing file. And if you go the Dropbox in the lecture files, you might also have your own trees file. If you do, please just use that one. Street trees, and then we are going to select the AutoCAD shapefile, so the shape source, so not the SHX. Click open, and then we'll plug this parameter into the imp @it component, the shapefile path input. The other input, of course, we need is the true or false. So we will grab a Boolean toggle. So we'll go to params, input, Boolean toggle. and we'll plug that into the true or false input. Now we can double click this Boolean toggle, set it to be true, and we can see we have shapes coming out. Right now that doesn't mean much to us. And we have features coming out, and this will mean a lot to us. And we will be using the genus names in this example to sort of choose what block we want. So essentially, now that we've imported in these shapefiles, we're going to use another component from @it to visualize them and parse them. So let's go to @it, go to shape, and then again we're using the data viz @it component. So now we have a bunch of inputs. First one is shapes, so we can take this shapes output from the imp @it component, plug in. Second one is filter specific feature, optional, we'll leave that blank. Filter by feature value, also optional, we'll leave it blank. Get value of specified feature only. We will plug our features into this. So this essentially is just gonna tell us, or it's telling this component, give us all the features information, we'll sort it out after. And I've just found that it's easier to sort it after the fact. So let's take our features, plug into get value of feature, and then take our Boolean toggle and we can plug into true or false. So it's sort of sorting everything, or it's triggering both components at once. Now in our perspective menu, you can see we now have the locations in 2 dimensions of street trees. Now remember, I cropped these in the City of Vancouver Open Data Portal using the polygon over the map technique. So refer back to class 1, the video, to see how to do that. So once we've done this, again, if you go to assignment 1's sheet, essentially you'll see that the second hand in is the Grasshopper file, just one. And mostly it's just, well, it's only going to be marked on organization. So if I want to get full marks for that file, what I'd do right now is I'd select these objects, I'd right click outside of them, I'd go to group, I'd right click the group, and I'd just simply call this importing in the trees shapefile, something to that effect. So it might seem a little bit, you know, quite simple to have to annotate it at this point, but I mean, you're going to use these components like maybe twice a year. And I guarantee you, regardless of how good your memory is, you will not really remember what data viz @it means, you know, 2 years from now. So it's good to sort of write notes to your future self. So now that we have that, essentially what we can do is we are going to look for the intersections between these points and the surface here. So if you remember, we left a layer called GHREF unsplit. So it's this unsplit surface. Essentially, this is where the GHREF comes in. So it's the Grasshopper ref, and we're going to look for intersections between these points, or rather rays from these points shooting up in this surface. We'll keep the points that intersect with this surface, and we'll call or get rid of all the points that don't. So the next thing we need to do is we need to reference this surface. So make sure your GHREF unsplit layer is on, and we're going to reference it. Now, one thing I will mention, if for some reason you've lost this layer, so let's say you forgot to create a GHREF unsplit layer and you only have these kind of finished split layers, what you can do is you can make a new layer. So why don't I make a new layer called GHREF unsplit 2. What you can do is you can, for example, copy this beach layer to the GHREF unsplit 2 layer. So copy objects to layer. I will isolate it. And then what I'm going to do is I'm going to use the command untrim. So I just typed untrim. I believe you can also go to Surface, Surface Edit, Tools, Untrim. And then I'll just select the edge I want to untrim, and you can see that this has all been untrimmed. From here, what you're going to have to do is you'll just probably want to grab the edges from other layers. So for example, you can grab your edges from this split surface, and you can use it to re-trim this surface here. So what you do is you would just go curve from objects, duplicate face border, you would go explode, like, you know, something like that. So what I'm doing is I'm just deselecting the curves that sort of join these two main pieces together. I delete the curves I don't need, and then you just go about re-trimming this curve. So if you do sort of lose your ref surface, as it were, you can always bring it back. It'll just take a little bit of legwork. So I just want to point that out because that's come up a few times in previous courses. Oops. However, since I do have my GH ref unsplit, I'll just use that. Just undo. Okay. Okay, good. So I'm selecting my unsplit surface. I'm going to go back into Grasshopper and I'm going to reference it. So to reference this surface, it's a surface, you can tell because when I selected it, it said one surface added to selection. We can go to params, geometry, and then we can go to surface. I'll put that down on the canvas. Having our unsplit surface selected, I'll right click this surface parameter and go set one surface. And we know it's set properly because it is now showing up red in Grasshopper, or when I select it, it is showing up green. So that means it's selected. Now, what we're going to do is we're going to look for an intersection between all these points. So essentially what we'll do is we have our surface here, and we have our little points, you know, around there. What our algorithm is going to be is it's going to say draw a straight line up from each of these points, and where you intersect. So there's one intersection there. Beautiful drawings, I know. There's one intersection there. If there is an intersection, then we keep those points and then we move them up to that intersection point. Or even simpler, we just keep the intersection point. So that's probably the easier way to do it. So that is sort of the algorithm we're going to use here. Okay, I know I did. Okay, so the way we're going to do that is we've referenced our surface here, and we have all of our points coming out of the data viz at it component. So you can see we have all these points coming out here. Now, what we want to do is we want to essentially, well, let's look at the way this data is organized right now. So let's go to params input, or sorry, params utilities param viewer, and let's plug our points into the param viewer. So it says data with 1636 branches. You can see each of these branches. This is the branch number right there. So 0, 1, 2, 3, 4, 5, 6, 7, 8, n equals 1. So there's one item in each branch. Essentially, we want to look at this data set as a whole. In other words, we want only one branch with 1636 items in it. So what we're going to do is we're going to flatten this. So I'm going to right click the point output. I'll go flatten. And now you can see that we have just the one branch. So a branch whose location is 0. And n equals 1636. So there's 1636 items within that list. So what we'll do now is we'll draw a line up from each of these points. and see if it intersects with this surface. Is a sort of intersection test. So I can just delete this. I just wanted to point out what I was doing there. So what I'll do, first I want to draw the lines that are shooting up from each of these points. So I'll go to curve, I'll go to primitive, and I'll go to line SDL. So line SDL is create a line segment defined by a start point, tangent, and length. So start, direction, length. The start is going to be the points that come out of data viz at it. So you can see we have all these short little points. The direction by default is 0, 0, 1, which is what we want. It's straight up. So x equals 0, y equals 0, 1 equals z, or z equals 1, so straight up. And the length by default is 1, so 1 meter. Now, we could change this length. So let's say we can change it to whatever, 100 meters, commit changes. But the kind of intersection we're going to use actually doesn't even care about the length of the curve. So we can leave it its default value of 1. And I'll explain what I mean when I say that. So what we're going to do is we're going to go to intersect now. And we're going to go to mathematical. And then we're going to go to surface line. So solve intersection events for a surface and a line. And I just want to check. I went brep line, but this should be fine. Let's see. You know what we're going to do? Well, let's see if this is going to be fine. So what we're going to do is we're going to take our surface that we've referenced. So that's this our ground surface, the unsplit ground surface. We're going to plug into the surface input of surface line intersection. And then what we'll do is we will take our lines SDL and plug into the line input of the surface line intersection. And then it might take a second, but then you can see what it's going to do is it's going to figure out all the intersections between the lines and the surface. So the reason why we didn't need to extend our little lines like so all the way up, so let's say by 100 meters to find these intersections here, was that we're using a mathematical kind of intersection. So in that case, what it means is that Grasshopper is just looking at the line as simply a base in a direction. So it's more thinking of it as a vector, as you know, as it were. So that's why you don't need to extend up these lines to you know, a length of 100. If you want to, you can. It doesn't make a difference. But, you know, maybe for visualization reasons you want to do this, but it really doesn't make a difference. If the surface were, let's say, below, it would still find the intersections because it's going to extend that line infinitely in both directions. So you can see it's still finding those intersections. So that's what the mathematical intersections do. If you only want to find the physical intersection between like a specific line as drawn and a surface is drawn, that's when you'd go to intersect, physical, and then surface curve. Always try to do mathematical intersections because they're faster. So that's why I opted for this first. So does anyone have any questions up to that point? Okay, so what we're going to do is we are going to select these three components right here. I'll right click outside them, I'll go group, and I'll just label this group here intersections between tree, points, and surface. So surf, shortened form. And at this point, what I can do is I can just preview off. So I'm just selecting all these components that precede the surface line intersection, right click outside of it, go preview off. So now you can see I just get these points. Now, if we look at the output of this surface line component, you can see we have curves, which is empty. And then we have points, UV points, so UV points being the position on the surface. So, if this was reparameterized 0 to 1. And then the normal, so this is the normal vector, so the straight up line at each intersection point on this surface. But what we're concerned about is the points. And what we're going to do is we're going to use the fact that it essentially has created new branches for each intersection. We're going to use that to create a calling pattern for other information. So what do I mean by that? Let's go to params, utilities, param viewer. So params, utilities, param viewer. So you can see that we still have data with 1636 branches, right? So the same kind of format that our points were in before we flattened it right here. In fact, we probably don't even need to flatten these points. You'll do the same thing. So you'll see point, 1636 lines intersecting with the surface. And essentially for each branch that we have going in, you can see that it either has 0 intersections, so n equals 0, or it has 1 intersection. So everywhere it has 1 intersection, that's a condition like this one there. But, if we're thinking of, let's say, this point way out here, it's going to shoot a line straight up. It's going to have 0 intersections, so it's going to give us this kind of result, n equals 0. Now, if you think about the component call, so if you remember what calling is, it's essentially calling or getting rid of items based on a pattern. So let's do a little example. So I'll grab a little panel like this. You don't have to follow along with this. This is just an example. I'll type a couple things into it. So I'll say apple, orange, lemon, lime, grape. And what I can do, sorry for the chem and not a lemon, what I can do is I can call it with a pattern. So I can go to sets, sequence, call pattern. The list I want to call is this list of fruit here. In the pattern, what I can do is I can essentially use a pattern that is, let's say, multi-line data. I can say true, so I want to keep the apple. False, I don't want the orange. True, I want to keep the lemon. False, don't like that lime. And let's say false, I also don't like that grape. And now you can see, of course, anything that's labeled with a false, aka the orange, the lime, and the grape, is not left in this list. However, in place of trues and false, what I can also do is I could also say 1, 0, 1, 0, 1. And this is essentially just shorthand for true equals 1, 0 equals false. True equals 1, 0 equals false. So it works the same way. So what we're going to do here is you can see that our intersections, we either have 0 intersections or 1 intersection. So we can use the fact that we either have 0 intersections or 1 intersections to our advantage and say length equals 0 equals false. So call data. The data that we're going to want to call will be the name of a tree, but we'll get to that later. But really what I want to point out right now is we can go to sets, and please follow along with this part. Sets, list, list length. We can take our points output, plug into the list input. We can flatten this result. And then let's grab a panel. So param input panel. And now you can see that our results are essentially the length of that list. So our first line, which was in its own branch, had 0 intersections. So you can see index 0 in our new list is 0. All the way down to, you can see here that branch with a path of 5 is now index 5, and its value is 1 because there is 1 intersection, n equals 1. we can essentially now use this list of 0 and 1s to call a pattern later on, which we'll do right now. But does that kind of make sense to everyone? The sort of using the length of intersections to create a list of 1s and 0s, and how 1s and 0s can also be used to call a pattern. So for example, we could plug this into our list of fruit and it would call everything. Does that make sense? Can I get one yes in the chat? Or if it doesn't make sense, please let me know even more so. Does anyone have any questions about that? Okay, thank you, Cicely. Essentially what we're going to do now, okay, Meredith says, what does flatten do? That's a good question. So flatten, if we look at our panel right here, I'm going to grab another param viewer. So I'll take the list length output, so our final component, I'll plug into a param viewer. Again, a param viewer can be found at param utilities param viewer. I'll plug that into the param viewer there. And you can see that data with 1636 branches. Essentially what that means is that this data, which is a length of intersection, is in its own branch. So Grasshopper likes to think of data as branches. So if we double click our param viewer here, there's a whole bunch of branches there. Essentially what's happening is you are saying each of these data items is on its own branch. So if this was a weird looking tree, these circles are data, each of them's in its own kind of branch. The way I like thinking about it is, instead of saying branches, I like thinking of these as boxes. So what we can say is there's 1636 boxes. I won't draw 1636, but let's say there's 4 branches, so 4 boxes. Each of them has one item in it. So there's our item of data, which is either a 0 or a 1. When we do some sort of manipulation or transformation to this data, since all this data is in its own box, it will perform that manipulation or transformation on each of these pieces of data in isolation. So in other words, it'll only look at this box, and then it'll look at this box, and then at this box, and then at this box. What flatten does is it gets rid of all the boxes and puts all the data in one box. So instead of 4 items in 4 boxes, we have 4 items in one box. So now when we analyze this data, let's say we want to do some sort of transformation, we're going to look at it all at once because it's in one box. Does that... I know it's a little bit abstract now, but hopefully kind of the following example will make it a little bit clearer. So the reason why we flatten is if I right click here, you can see now all of this information is in one box. I'm trying to think maybe what we'll do right now, because I think this is maybe something that's good to review, is let's take a break. Nicholas, for your information, we take a break somewhere around the midpoint of the course for, let's just say, 5 minutes in this case, or let's come back at 7:30. We'll pick right up, and I will in that time sort of search for a example that maybe can explain that tree flattening business in a little bit more intuitive way. Oh, and also Nicholas is coming in with the good information, so maybe we can go through this a little bit when we get back. So I'll just take a few minutes to do that at 7:30. So I'll see you all at 7:30. Okay, so yes, my mic is back on. I'll do a quick review of sort of the anatomy of data in Grasshopper, so the way that it's structured. So if we look at what's going on here, so I've just sort of quickly drawn this up. I have an upper row of points, which I've referenced. You don't have to rebuild this. And I have a lower row of points, which I have referenced in Grasshopper. You can see here that what I've done is I've attached a panel to the upper row of points as well as the lower row of points. I've also attached a param viewer to both the upper row and the lower row. In fact, I've attached 2 param viewers to each of these. So if you aren't certain about the param viewer, again, it's under Utilities Param Viewer, and it's going to tell you some textual information about the data tree. But if you double click it, you'll also get the visual kind of representation of the data tree. So that's what's going on here. So it's the same thing. It's textual and then visual. Now, if you look at this upper row of points and you look at what the param viewer is saying, it says data with 1 branch, 0, n equals 4. So essentially, what's happening here is there's a few different numbers that we can see. So the first number we see here is this 0, and that is called a path. And essentially what that means is that all of this data is stored in path 0, or if you want, branch 0. So you can think of it 2 ways. You can either think of it as a box. So I've sort of drawn a box here. I guess it's upside down. But a box like this storing all of these points with a address of 0. Or you can think of it as a branch, a tree of a branch 0. The other thing you can see here is n equals 4. So that means there's 4 items in one branch. If we look at the panel right here, you can see that the path 0 is up in the upper right-hand corner. So this is the location of the branch or box that you want to, or that's under question. And then you can see that all the objects within each branch all have their own location within each branch, and this is called the index. So you can see that the first point, which is this left point here, has an index of 0, then index of 1, then index of 2, index of 3. So you can see 4 points in one branch. If we right-click the upper row and go graphed, what is happening now is that we have 4 branches. So I'm just going to preview on something I drew here, just so we can sort of visualize the boxes. Again, I like thinking of boxes more than branches. But essentially what's going on here is that now each of these points is in its own branch. And its own branch has a path that has 0, 0, 0, 0. So that first 0 in the path relates to its original branch, or we can think of it as its original box. And then the second number in that path relates to a new box or a new branch. So the previous index of 0 goes to branch 0. The previous index of 1, so right there, goes to a path of 1. And then likewise, an index of 2 goes path 2. An index of 3 goes to path 3. Now, the reason this is important is that Grasshopper is going to try to match data at the lowest possible level that matches. So what that means is if this upper row of points is, let's say, flattened, so flattened equals only one branch, only one box, Grasshopper is going to match these points, the upper row and the lower row, on a index level. So it's going to say, okay, these both have one path, so they each have one box. So I can hide these little boxes. They each have one box. So since this box matches, we can just sort of disregard it. Now let's match these points at a point-by-point level, right? Now, if we, let's say, graphed the upper row, what Grasshopper is now saying is, oh, wait a second, there's 4 branches here, 1 branch here, so we're not even going to worry about moving into those branches. We're just going to match at a one branch to one branch level. So what's happening is branch number 1, so this branch here, which contains 1 point, is matching with 1, 2, 3, 4 points, because it's matching one branch to the one branch. Now there's another branch, so branch number 2 contains 1 point, it's matching with all the points down here. Branch number 3 is matching with all the points. Branch number 4 is matching with all the points. If we graphed the lower row as well, now Grasshopper is matching branch to branch. So it says, okay, there's a branch 0, 0, a branch 0, 0, a branch 0, 1, a branch 0, 1, so on and so forth. So we get these matching, somewhat vertical lines again. So it's matching branch to branch. It's not able to create a perfect match when it's going grafted to flattened, and if both of these data sets are flattened, then it's matching item to item within the singular branches. So that's kind of an overview of the terms. It's one of the more abstract things in Grasshopper. If you have programming experience, you can think of it as lists of lists. So if that applies to some of you, that sort of is just a way to think about it. That's actually probably why I think of boxes, because I'm just thinking of, brackets, essentially. But for everyone else, this kind of stuff will eventually make more and more sense as you work through it. Nicholas also posted some excellent links. The second one looks especially promising, so check that out as well. And Nicholas, if you could actually just copy those into the main folder, the Dropbox, that would be excellent, because this looks good. So just go through this. If you have any questions, feel free to reach out to Nicholas or myself. So moving on from this, though, sort of back into trees, not the Grasshopper kind, but the real life foliage shade giving kind. Essentially, we've now figured out the intersections, and we have essentially converted those intersections to zeros and ones. So points that made 0 intersections, if we measure their branch length, it gives us a 0. If they made 1 intersection, we measured their branch length, that gives us a value of 1. So that gives us this list of zeros and ones. Now, in my previous example, we were calling or getting rid of apples, oranges, limes, what have you. What we're actually going to do is get rid of feature values. So let's go back into this importing the trees shapefile right here. So this is the first group I made. And let's go to the features list right here to kind of figure out what we want. So let's go to params, input, and then panel. And I'm going to extend this panel so I can see all the information attached to these points. Now, there's lots of things that you could sort of glean from these trees. For this example, we're going to do 2 pieces of information. So the first one we're going to glean is the height underscore rang, so height range. And then the other one is the genus name. So first, let's choose the height range. So height range is number 14. So let's go to sets, list item. So that's sets, list item. And what this does is retrieves a specific item from a list. So if we look at the at values, so these are the attribute values, or maybe it's attached values. Essentially, they're the values associated with the points. Essentially, what we're going to do is we're going to use the list item to choose number 14 from all these branches. So you can see that each point that has come out of this overall field of points has a bunch of values attached to it. So what we can do is we can take our at values, plug into the list input of our list item. the index. Again, index is this number on the left-hand side, so it's the position within a single list or a single branch. In this case, is going to be 14, height range. So what I'm going to do is I'm going to go to params, primitive, integer. I'm going to plug the integer into the index. So it's giving us an error because, you know, there's nothing in here right now. But then what I'm going to do is I'm going to right click this integer. I'm going to select a little name at the top here, and I'm going to call this 14. And then afterwards, I'll just put height underscore rang. And this is just to remind me which value I'm choosing from this list. Now remember, when I change the name, even though I've included a 14 in the name of this input parameter, I'm not actually saying a value. So what I need to do is click this component, go to set integer, and then type the value 14. Then click the commit changes button. And now you can see that the list item coming into index is 14. We don't need to worry about the wrap right now, so we can leave it as default true. So what this is doing, and maybe this is a good time to sort of explain the list item 14 right here. So if we look at, I'm just going to grab a param viewer. You don't have to follow along with this, but I just think this is a good opportunity for learning. If we look at the param viewer, you can see that we have data with 1636 branches. Each of those corresponds to one of the 1636 points here, right? And each of these branches has 18 pieces of data. So essentially what's happening is that each of these points, or the branch corresponding to it, has the tree ID, the civic number, the standard street, the genus name, species name, cultivar name, etc., up to the date of planting. If we're saying choose index 14 from each of these lists, what we're doing is, instead of looking at all of these items in one long list, so it's not that we have this list repeated 1636 times. What's happening is we have one box with an address of 0, and then all of these values go into box 0 corresponding to, down there, point 0. Likewise, we have box or branch 1 corresponding to point 1 that's out there somewhere, or point 1 coming out here. And again, we have all of these values in there. So when we choose list item 14, what we're doing is we're not saying 14 out of all of these boxes. We're saying choose 14 from here. So number 14 from this list, number 14 from this list, you know, number 14 from the third list, all the way to we get to, so ... all the way to box or branch 1635 will be the last one, right? So that's also filled with that stuff, and we're also grabbing number 14 from that final list. So that's just an instance where the data management of Grasshopper, we can use it to our advantage to sort of create a meaningful definition and a meaningful way to organize information. So that's what we're doing. So if we grab a panel and we plug the list item output into that panel, you can see we get a bunch of values of 1, 3, 5, 2, 3, 3, etc., etc. Now, those numbers right now, they don't seem intuitive to us. Maybe they do, because we actually did this last class, so this will be a quick review. But essentially, we need to go to the City of Vancouver Open Data portal to see what these numbers correspond to. So if you remember, what I'm going to do is I'll just type in COV Open Data, and then I'll type in street trees. So street trees, City of Vancouver Open Data portal. And if you want to follow along with this, I'll just copy this into the chat. And if we scroll down to the bottom of the street trees section, you can see that we can click Dataset Schema, click to expand, and this is going to tell us what this means. So 14, height rang, scroll down until we see height rang, which stands for height range ID. And it says that 0 to 10 for every 10 feet. Example, 0 to 10, or 0 equals 0 to 10, 1 equals 1 to 20, 2 equals 20 to 30, 10 equals 100 plus. So what we need to do is we need to figure out a like simple expression to convert, for example, 0 to 10 feet. So the way we're going to do that, and this will be reviewed from the first class, is since 0 is going to equal 10 feet, we'll just go for the higher value in each of these little ranges. We can say 0 equals 10 feet. We can say 1 equals 20 feet. 2 equals 30 feet. So on and so forth, all the way till 10 equals, we'll say 110 feet. Now, we're not saying 0 equals 0 feet because a lot of trees are below 10 feet, and it's better to err on the side of having a too tall tree that actually exists than having a bunch of null item 0 length trees in Grasshopper. So that's why we're doing that. So the little formula we can use to come up with this is we can say where x is the value that's output by this component. So the height range outputs a value between 1 and 10. We can say x times 10 plus 10. So if we think about this, 0 times 10 equals 0 plus 10 equals 10. Likewise, 2 times 10 plus 10 equals, this is 1 times 10 plus 10 equals 20. And likewise, 2 times 10 plus 10 equals 30. And all the way till, this will also hold here. So 10 times 10 plus 10 equals 110. So that is good. Now, the other thing we need to do, though, if you remember, is we need to also convert these to meters, because our Rhino file's in meters. And if we look at the City of Vancouver height range ID entry, it says 0 to 10 for every 10 feet. Unfortunately, Canada mixes and matches, imperial and metric. The country does a lot of things right. Measurements is not one of them. So in this case, we need to make that conversion. So it's about 0.3, or you could always just say 1 foot equals meters. So 1 foot equals 0.3048 meters. So then what we can do is we can essentially just, to convert this after the fact, we can say x times 10 plus 10 times 0.3048. So this is how we convert it to meters in the end. So to do that in Grasshopper, what we can do is we can go into our, I'll just delete this panel here, out of our list item. We can go into our maths, then script, then evaluate. So math, script, evaluate to create a kind of simple expression. And what we can do is we can zoom into this evaluate component. We can click the little negative on the white circle here to get rid of this variable y. We only need one variable.
We don't want to have to write variable x over and over and over when we're using this component. So what I like doing is just swapping the variable x for x. So what I did there was I just right-clicked on the input variable x, and then I changed its name to be just x, lowercase x, like so. And then what we're going to do is we're going to take our list item output and plug into the x input in our evaluate component. Now what we can do is we can double click on this component where it says evaluate, and now in here we're opening up our expression designer. So if you remember from before, what we're going to do is we're going to say x times 10. So for example, 0 times 10 plus 10. So this gives us our value in feet according to the city of Vancouver. So 0 times 10 plus 10 would give us 10. And then we need to convert it afterwards to meters because our units are in meters. And if we remember, we saw that 1 foot equals 0.3048 meters. So I can just copy this value again. I'll copy it into the chat if need be. So we can just go times 0.3048 meters, and that will give us our value in meters. I'll copy that into the chat as well. And I'll click OK. So now all of our zeros and ones, twos, threes, etc. that's coming out of our list item. So that's selecting the height range. Now what that's giving us is actual values in meters, approximately, of the trees for all of these points. So what we can do is we can select these components here. I'll group them. So that's our number 14 that we've set, the list item component, and the expression evaluate component. We'll right click the group and we will just call this tree heights in meters. So what I'm going to do is, I'll just leave that there for now, is if we look at our tree heights, why don't we flatten the output of this so we'll look at them all as one list. You can see that we have 1,636 values, and each of these, they're corresponding to all these points over here. So I have 1,636 points here, and as we know, not all of those points intersect with our surface, right? In fact, it's only 225 points that actually intersect with this surface. So if you think back to our list length component, essentially giving us a bunch of zeros and ones, zeros if there was no intersection, one if there was one intersection, we can use these zeros and ones to call this list here, because we only want the tree heights that intersect with this surface. So what we can do now is we can go to sets, we can go to sequence, we can go to call pattern. So that's sets, sequence, call pattern. The list we want to call will be our tree heights. So let's plug our tree heights into our list. And the call pattern can be our trues or our zeros and ones coming out of our list length component. Again, make sure that both of these outputs are flattened so they both have the small downwards facing arrow. To flatten something, you just right click on an output and click flatten. So put the list length output into the call pattern input, and now you can see that you won't see anything changing here because we're just calling the heights that we don't need, so they're not actual objects. But you can see if we hover over the list output, we now have 225 tree heights that correspond to the 225 points that we have intersecting with our surface right there. So what I'll do now is I'll just preview off all the data that's outside of sort of our most recent data. So I'm leaving preview on for the surface line intersection, and everything else I'm kind of leaving off. So does anyone have any questions about that? Okay, so we have our heights, we have our tree locations. Essentially what we're going to want to do now is maybe what I'll do so it's not so abstract. We can... I'm just thinking if I should modify this. Let's do a version of this first where we're just representing the heights of the trees by lines, because I think it would be good to take this out of abstract land and sort of put it into something we can see again. So let's just do a quick mock-up of the tree heights essentially. So we have our heights here and we have our intersection points. Let's just very quickly just go to curve, primitive, line SDL. And now what we want to do is the start is going to be our surface line point intersections. But as you can see, they're grafted here. So what we're going to want to do is we're going to want to right click our start input, go flatten, take our points output, plug it into the line SDL. So now you can see we have all these little lines. They're moving upwards from our intersection points. The second input for a line SDL is direction. Trees mostly go straight up, and by default the direction is straight up, so we'll leave that. And then the length by default is 1, but we will switch the length to be our call pattern output from our tree height in meters, so we'll plug that in. So now the reason why I'm doing this is just so we can kind of get a sense of our tree height. So if you look at this, you can see there's variation in tree height. So this, of course, won't be our final, these won't be our final trees, but I just wanted you to see that this data does have meaning. So that's what we're representing there, and that's why we called these heights. They correspond to each of these intersection points. So what we can do now is this called pattern. Maybe what I'll do is I will just preview off my line SDL we just made, so we sort of saw what will preview the trees. I'll just preview that off because we're going to work on something that's a little bit more text-based again. So we called the heights, but now what I want to do is I want to use the genus name to assign a block. So essentially what we're going to do, why don't we first just grab the genus name? So we grab the tree height in meters. Let's grab the genus name. So let's review how to do that. Again, we're going to go to sets, list, list item. So sets, list, list item. We're going to go to our attached values output. And we're going to set a new index. So our genus name is has an index of 3. So 0, 1, 2, 3. So the index we want is 3. So what we can do is we can go to params, primitive, integer. So integer being a whole number. Let's right click this integer parameter. Let's call it 3. Genus name, and then let's go to set integer, and the integer is going to be 3. So remember, naming it does not set a value, it's just naming the container that holds the value essentially. So genus name integer equals 3. We'll take this 3 and plug into the index, and just like we did right here at the end of our expression, we will flatten this data. Now let's look at what's coming out. So let's go to params, input panel, and the output is all these genus names. So we have some acers, some tilias, another acer, a pyrus. Again, I'm not going to pretend to know what most of these or any of these mean, but what I am at least assuming, it looks like pyrus equals pair, so I'm just looking up pyrus genus right now. The acer genus, for example, it looks like it is a bunch of different maple trees. Is that kind of right? Can one of the landscape architects confirm if that's kind of right? Yep. Okay. Thank you so much, Nora. So essentially, this does have some good utility in that, an Acer tree is essentially all the maple trees. The Tilia, what is a Tilia? A Tilia is one of these trees that kind of has the rounder leaves. So essentially, what's going to be useful about this is we can use these genuses, to essentially organize which block we use. So you can imagine that we could make a block for each kind of genus. We're only going to work with these 2 blocks here, but I think it's a good way to sort of think about organizing data. So I want to go into a topic that's a little bit of a specialty, but I think that it's super useful for analyzing things like program, or in this case, analyzing different types of trees. And that's using text manipulation in Grasshopper. So this is a little bit more of those like intermediate topics. But essentially, the reason why it's going to be useful in this is we essentially want to see how many unique genuses there are in this in all the trees that we've sampled, right? So the way we do that is we create what's called a set. And simply put, a set is a list of unique values. So you can see that this list right here has some repeated values, has a bunch of acers, has a few quercuses, so on and so forth. So what we can do is we can create a set. So to do that, let's go to sets, set, create set. So that's set, create set. Take our list item, which has been flattened. So you can see 1,636 items in one list. Plug it into the list input of create set. And what this is going to do is if we look at the output, it's going to tell us all the as it were, unique values is. So these are all the different kind of genuses that are compared, or they're included in this big set of points in this data set we're working with. So this is useful to know. What we're going to do, though, before we sort of work with this further is, of course, we don't really care about the kind of trees that are outside of the bounds. So if you think about it, we have all these points. Maybe there's some genuses in these points that aren't included in these points, so we want to call this list first. So if we think back to our list length here, we called a pattern of the tree heights based on this list length component, so we're going to do the same thing with the genuses right here. So essentially what we can do is, again, we can go to sets, sequence, call pattern again. The list we want to call this time is the genus values. So let's take our list item here, plug into the call pattern, the list, and then the call pattern will be our list lengths from up here. So let's plug the list lengths in here. And now let's take this call pattern output and plug it into our create set input to sort of see if we've reduced any of these names. And yeah, we have. So you can see that this area that creates intersections with our ground surface here, there's less than half the amount of variation in tree genuses as there are in this entire segment of Vancouver. So that we've sort of reduced it this way. Now, why don't we group our data at this point? So let's go back and sort of group some of this. So I'm just going to group the genus name. I'm going to maximize this so you can all see it a little bit better. So I have my genus name. That's essentially just an integer 3 that's choosing the third item in the list item, or in the attached values. So list item component there. We're calling those items with that same list length component that's coming out of the point intersection test. And then we're creating a set, so a list of unique values of those tree names. So we can select all those things, we can group them, and we can simply call this maybe list of tree genuses. I don't know if that's the plural, but it works. So essentially what we've done now, if we think about it, I can preview off the data viz at it. If we think about it, what we've done is we've called away all the points that are outside of the bounds of this surface. We've called away all the tree heights that are outside the bounds of this surface. So that, remember, that's what we use to draw these kind of preview height lines. And now we've called away all the genuses that are essentially outside the bounds of this surface. So what I'm going to do is now I'm going to start using blocks. So if you remember earlier in this lecture, we brought in these two blocks. What we're going to do is we're going to start assigning these block values to these genuses. So for example, wherever there is a prunus genus, and I'm sorry, landscape architects, if I'm sounding like an absolute idiot by saying wherever there's a prunus genus tree. That's probably not how one talks about these things, but wherever there is a tree of the prunus genus, we can say, okay, insert block 1. So let's say that's the case right here. Let's insert block 1. Let's say that's also the case here. Insert block 1. Wherever there's a quercus, insert block 2. Wherever there's a betula, let's say insert block 2. Wherever there's a liquid ambar, insert block 1, and so on and so forth. So you can imagine that you could have 16 blocks, 1 block for each of these genuses. For our case, we're just going to insert 2 blocks. So we're going to sort of just go back and forth. So to do that, let's go to Heteroptera. So Heteroptera instance manager, essentially. And let's first figure out what blocks are in our file. So let's go to blocks list. And essentially, if we grab a panel, so a fast way to grab a panel, I'll start using this shorthand, is just to double click on the canvas and type panel. Take our definitions output. You can see that I have 3 blocks in this file. So the first one is public streets, AutoCAD, OD4. So this is from the City of Vancouver Open Data. It's probably some 2D block. You could go and delete this, clean up your file. For now, we can just ignore it. What we're interested in is tree 01 and tree 02. So what I'm going to do is I'm going to create a new panel. So I'll double click on the canvas again. I'll type panel, and what I'm going to do is I'm going to make a list of trees. So essentially, I'm going to say prunus equals block, or I'll say tree 1. Quercus equals tree 2. Betula equals, let's say, tree 2. So we'll choose whatever, we'll choose one of these blocks for each of these entries. I'm going to right click on this panel I'm getting out of my block list component. I'll go copy data only. I'll double click on this second panel I just made. I'll go Control V to copy it in. I'll delete all this AutoCAD FEME block 1 stuff. I'll make sure there's no spaces before or after this. I'll click out of the panel. The other thing I want to do is right click this panel and click multi-line data. And what this is going to do for each new line, it's going to assign it a place in the list. So now you can see tree 1 corresponds to item 0. Tree 2 corresponds to item 1. And what I can do is I can keep repeating these things. So, like so. And what we want to do is just make sure we have as many blocks referenced as we have genuses. So let's get rid of 4. Oh, need to get rid of 1 more. So now you can see what's happening. Wherever a prunus tree is specified, we'll put tree 1, which corresponds to this block. Wherever a quercus tree is specified, we'll place a tree 2, or this block right here, and so on and so forth. So you can imagine that Instead of this, you have defined a block for each of these entries, and then, you know, maybe your list looks something more like this, so on and so forth, where you have, you know, 1 to 8 and then 9 to 16. So essentially what we're going to do now is we are going to we're going to replace these items with these items here in this called list. So what we'll do is we'll go to sets, and then we are going, we're going to go to sets, text, replace text. So replace all occurrences of a specific text fragment with another. So sets, text, replace text. The text we're going to operate on is our called pattern in our list of tree genuses group. So this is the list of, in this case, 225 genuses that corresponds to the 225 points here. So this call pattern, I'm going to plug into the text input of replace text. Fragments to replace will be these genuses here. So that's why we chose that's why we created a set. So we wanted to figure out all the unique text fragments to replace. So I'll plug that into find. And replace will be the name of the block that we want to replace each instance of a genus with. So in this case, it's this alternating trio 1, trio 2, trio 1, trio 2, and we'll replace that like so. So now you can see instead of a Quercus, oh, why isn't that working? Instead of a find, replace, let's see why that isn't working. I just need to refer to my notes. Interesting. Sorry, I'm just referring to something's wrong. So I said list length, series, replace. Oh, I see. Okay, so for some reason it doesn't like replacing with these box files. Oh wait, replace text goes to replace members. Oh, excellent. That is it. Oh, thank you so much, June. Sometimes it's just been a long day. So that's in sets. So sorry, I was thinking of the wrong component. There's a lot of them. Instead of replace text, what we want to do is we want to go to sets, and then replace members. So replace members in a set. Phew, thank you so much. So again, let's redo that. So the set we want to operate on is the called pattern right there. Plug that into set. Find is going to be the set we've created out of this, and replace is going to be the trio 1, trio 2, trio 1, trio 2, etc. And the result now is what we want. So you can see wherever there is a Quercus, for instance, it'll be tree 2. So Quercus is these three right there, and you can see it's replaced with trio 2. So again, you want to use replace members. So again, thanks for your eagle eye. So that's good. So essentially now we're defining our blocks. So what we can do now is essentially we can start placing these blocks on each of these points right here. So the way we're going to do that is essentially we're going to do a couple things. So what we will do is I'll try to draw this out, is we will look at the width and the we'll look at our two blocks right there. So there's tree 1, there's tree 2. For each of them, we'll look at its height. And then what we're going to do is we are going to scale it based on the height of each of these points, right? So we already know that each of those points has a certain height associated with it. So let's say the height at the point is that, like that. We're essentially going to scale the trees by a certain fraction. So we can just work on it that way. So what we can do is let's first figure out the heights of these trees. So what we're going to do is we're going to go to Heteroptera. We're going to go to Instance Manager. And then we're going to go to block decompose. So Instance Manager, block decompose. And essentially, you can see that what this does is, given a few blocks, it's going to give us the objects, the attributes baked into those objects, the bounding box, which we're going to use, some good stuff. What we need to do now is to instance reference definition. Essentially what that means is we just need to reference these blocks. There's a few ways of doing it, but I want to show you one that's kind of interesting because it kind of adds a new primitive input to your Grasshopper. So what I mean by that is if we go to params, primitive, and then block definition. So this is new from since you installed Instance Manager. So again, primitive block definition. We can right click this and go set multiple Rhino blocks. And what we can do is we can select both of those Rhino block objects. So block or tree 1, tree 2, hit enter. You can see if we hover over this, it's going to say tree 01, tree 02. And we're going to plug that into the definition input of block decompose. Now, right now we're not seeing anything, right? And it doesn't even look like anything's selected. Now, the reason why this is happening is that this component, it will place your block at the location in which it was originally built. So in the case of our blocks, which we've referenced from another Rhino file, these trees were built on the origin point, so 0, 0, 0. So let's say we were to, for instance, let's say just draw a line in our Rhino window, and then draw the end of this line at 0, 0, 0. I'll hit enter, and I'm just doing this so I can zoom in on this end of the line. You know, there's lots of ways I could have done this. I could have drawn a point. Maybe that would be a better way to do it. Anyways, yeah, why don't I just do that? So I'm just gonna draw a point there and then zoom in on it. So zoom selected. You can see that this component is indeed referencing those blocks. It's just placing them where they were originally built. So if you're using this component and it doesn't look like anything's happened, rest assured that it has. It's just that your trees or whatever other object you're referencing that's a block is probably placed at the origin. So now let's go back to the task at hand. Essentially what we're going to do, you'll see that there was those bounding boxes there. What we're going to do is we are going to move those bounding boxes to each of these points. So essentially, what we will do is we are going to you know what? Yeah, we can. Yeah, so what we're going to do is we're going to decompose these boxes, and then we will move them to these locations here. So let's first go to surface, and then analysis, and then we will go to deconstruct box. The bounding box, we're going to put our bounding box output's going to go into the box input of deconstruct box. And this essentially is just going to allow us to define a few things. So it's going to give us the dimensions of the box in Z, aka the height, and it's also going to give us the plane of the box. We're mostly just going to deal with the height. You know what? Sorry, I'm just thinking about this. I think that even though we did put the blocks into the block decompose object, I do think that the better way to do this is just to take our replace members result and put it into the block decompose. So even though I want you to see that, it also sort of took me away from my notes. So sorry about if any confusion arises, but what we will do is we'll take the replace members and plug into the block decompose. So it's going to take a second because it's going to be solving for that block, but times 225. But I think this is a more straightforward way to do it. So essentially what's going on here while it's solving, yours will take a minute as well, is we're taking our replaced members, so that's replacing all of our genuses that are related to these points, and giving us the block that corresponds with each genus. So you can see we have 225 trees, each of them has a block name, and then each of those blocks we're getting its box and the objects in that box, and that's the reason why it's taking a little bit longer to solve, because the objects are being solved for each iteration of this tree or this this block. So what we're going to do now, finally, we're going to take the boxes, we're going to move them to each of these points. So you can see each of these bounding boxes out of the block decompose. These bounding boxes are going into the deconstruct box, and each of these has a plane. So what we can do is we can just draw a vector from essentially the planes of these bounding boxes to these points here. So essentially what that's going to do is it's going to draw a point from the origin, since all these bounding boxes are at the origin, to each of these points here. So let's do that. So we can go to vector 2 point. Point A is going to be the plane from our deconstruct box. Point B will be, if we go up here, it will be to our tree points here. Now, what you want to make sure to do before you plug your tree points, they're coming from the surface line intersection. So they're coming from the surface line intersection. Sorry, that name keeps disappearing. What you want to do before you plug it directly into point B is you want to right-click the point B input and go flatten. So let's take our points output from the surface line intersection, plug into point B. Essentially, it's going to draw all these vectors. If we want to visualize these vectors, what we can do is we can go to display. We can go to vector, vector display. The anchor is going to be the point B's. So again, let's right click the anchor and go flatten. The points output, plug into the anchor's input, and the vectors will be the vectors coming out of our 2 point vector component. And you can see what's happening is the origins of these blocks are way off in the distance, so out at 0, 0, 0. And what they're doing is they are moving towards these points. So these vectors are backwards, actually, so you can also put the planes as the anchors as well, and that's going to show you moving from the origin to these points, so you can see the little arrows. So these are essentially movement directions, so they're vectors. Now all we need to do is we need to move the boxes to those points. So let's go to transform, go to Euclidean, and move. The geometry we want to move are the bounding boxes. So out of your bounding box block decompose, you want to take the bounding box output, plug into geometry. The motion will be your 2-point vector. And now you can see what happens is our vector, or our bounding boxes are now on our site. So that's great. So now why don't we group, sort of go back and clean up this definition. So essentially what we're going to do is we are going to group together perhaps the, I think what I'll do is I'll just group the all my block list here. So I'm going to right click this panel for future reference, the one that has all the trees 01s, 02s on it. I'll right click it. I'll call it blocks to replace genuses, like so. And I'll just group that with the replace members component. And then I will right click on this group and I will call this replacing genus names for blocks. And then I have my block decompose here. And then my deconstruct box, I'll group these two components together. I'll right click these two components, this group, and call it getting block bounding boxes and box heights. And then the vector 2-point in the move, I'll group these together, and I will call this moving boxes to points on site. Okay. So now what we need to do is we've moved all these boxes to the site. We just want to scale them by the proper height. So if you remember, we have the height up here. So the called pattern coming out of the tree height in meters group. We just need to scale these boxes. So what we're going to do is for each of these boxes, we've decomposed them. So we've used their plane to move them, but now we can use the Z value as their height to scale them. So what we'll do is we'll go to maths, domain, deconstruct domain. So you can see that these are the Z dimensions of the box. So there's two values there. A box, will start from, let's say, 0 in the Z axis and go up to, let's say 14, for instance, and then that creates a box like that. So that's what this domain means. So a domain of 0 to 14 essentially means the box starts at 0, has a height of 14. So what we want to do is we want to take the domain end and subtract the start. And you can see that for the most part, the start's 0, but for it looks like block 1, the start is actually technically negative 0.0000252. So we want to take that into account. So we'll just go to math, operators, subtraction, subtract the start from the end. So the end goes into A, start goes into B, so end minus start. That gives us the height. So maybe I group these together and call this height of blocks. And now what we can do is we can divide the height of the trees by the height of the blocks to give us the number to scale these blocks by. So what we'll do is we'll go to Maths, Operators, Division. The call pattern that's coming out of our tree heights and meters group, so this is the list of all the tree heights, will go into A. So we're going to divide the tree heights by the current block heights. So the block heights are here. And this is going to give us the scale factor. So you can see that the tree height is 1.2 times as high as, let's say, this block, for instance. So now what we can do is all our moved blocks, we can go to Transform, Affine, Scale. So the geometry we want to scale is the boxes we've moved. So let's move them, or let's put the geometry output into the geometry input of scale. The center of the scaling is going to be the intersection points, so these points down here. So to do that, let's right-click the center input, go to Flatten, because we want to consider these intersection points as one list. Scroll way back out, go to our surface line intersection, take the points output, drag it into the center scale input, and the factor, so you can see by default they're scaling by a value of 0.5. The factor is going to be the division result. So the division result, let's plug into factor. And now you can see that they are scaling by the proper factor. So now we can preview off these things. And now we have our scaled boxes. So let's group this division and this scale. I'll right click that and call it scaling trees to proper height. Now, I know we're 2 minutes over. It'll just take 2 more minutes to wrap this up. So let's hold in there. So essentially, the few last things we want to do is one, we want to randomly rotate these boxes, because if we array the trees into these boxes right now, it's going to look very artificial. Trees do not all grow in the same, I guess, orientation. Although maybe they do. They grow towards the sun, but it's not apparent at least. So we are going to randomly rotate these. So to do so, let's simply just go to, let's create a bunch of random numbers. So let's go to Sets, Sequence, Random. So generate a list of pseudo-random numbers. If you're interested in why it's pseudo, send me an email. The domain of the randomness that we want to rotate these trees, let's say 0 to 180. So let's just right click on the range input, go to set domain, and change it to 0 to 180. So I just added a little 80 to that one that's right there. The number, so the list of values we want, what we can do is we can go to sets, list, list length. So sets, list, list length. We can just measure, for instance, the boxes. We can measure anything, really. We can measure the scaled boxes. So how many scaled boxes do we have? So take the scale output, the geometry output, put into list length. It's going to tell us that we have 225 boxes. Let's plug that into number. And then the seed is, we can just use a number slider. And this is just a value that will change the randomness. So to create a number slider, a quick way of doing that is double clicking on the canvas and then just typing, let's say 0 less than, and let's say 2000. Hit enter. That creates a slider between 0 and 2000. Plug that into seed. And this is just going to randomize your numbers. So we'll see it in action when we actually rotate it. So now what we can do is we can go to Transform, Euclidean, Rotate. The geometry that we want to rotate are our scaled boxes. So the scaled geometry output, plug into geometry input of rotate. The angle, let's right click it, set it to degrees. So right click, degrees. Then take our random number generator, plug into the angle. Now the plane that we want to rotate these trees on will be the intersection point for each tree. So again, let's right click the plane input, go to flatten. And then let's go to our surface line intersection. So we're using this one a lot. Essentially, it's these intersection points. Take the points output and plug it into the plane input. And now if we preview off our scale trees, you can see that they are randomly rotated. And if we change the seed right here, you can see that they're sort of randomly rotating in different ways. So if you're not happy with the random rotation, you can sort of shake it up this way. Okay, so now just one more thing to do. If we go back to our replace members component, we have a set of all these trees 1s and 2s. All we need to do now is go to Heteroptera, go to Instance Manager, and then go to Insert Block by Box. So fit and place an instance object into a reference box. So Instance Manager, Insert Block by Box. The definition is going to be our replace members output, aka our list of trees. So the result, plug into the definition. The transform box is going to be all our rotated and scaled boxes. So our rotate output, the geometry output, plug into the transform box. And now you can see the component turns gray, which means there's no errors. And you'll notice that nothing happens, and that's because this component's kind of unique in that the last input's a Boolean toggle, and when you set it to be true, it actually bakes the blocks. So let's go to params, input Boolean toggle, and then let's put that into place. And now you'll see what happens. Maybe now's a good time to save your file. So if you haven't, Control S. If you double click place, you'll see that the trees place and they are scaled and rotated. So if you want to make a change, this one's a little bit different. You can just go Control Z in Rhino. You'll get rid of them, make your change, maybe rotate them a little bit differently. Make sure that false is checked, otherwise they're going to keep on placing. Double click true, and then it's going to bake again. Double click false to turn this component off. So it's kind of interesting because if you look at it, it's placed all these different trees. It's placed it based on the genus name. So like I said, right now it's only 2 trees for, I think it was 13 or 16 genuses. You could make 13 blocks for 13 genuses if you want to. The good thing about this, oh, and the layer select is default. Yeah, so what I would do is, here, why don't I go through that again? It doesn't really matter. What I would do is I would actually make a new trees layer. So that's a good question. So I'd just go new layer and I'd put trees or blocks, what have you. And then in that case, when I would set the trees layer as the current layer, set that to be true, set to be false. And now if you select the objects on, oh, it doesn't bake to that. So yeah, I guess it does bake to the default layer. So that's kind of strange. I think that maybe the optional block instance attribute might be able to fix that. Let's see if we can work into that. Instant Manager, let's go to attribute. I don't know if we want to get into this.
Attribute build maybe.
Yeah, Maybe there's a way to do it. It's attribute build. Oh, there we go. Attribute build. So if you want to change this, what you could do is you could change the layer right here. So for example, I could make a trees layer, and then I could type in trees. I'm not sure if it's case sensitive, but trees, plug into the layer. So again, this is in Heteroptera, Instance Manager, Attribute Build. So the attribute now says layer trees, plug that into attribute, optional. And now in Rhino, I'm just going to undo that place. If I double click true and then select trees, there, then it is baked on this tree layer. This has given me an idea what you could do if you really wanted to is you could probably go back to your genuses names right here. So you have your call pattern list of genuses. You could probably plug that into the layers. Yeah. And so what happens if you plug that into the layers is now you have all these trees. If you select Prunus, then here are all the Prunus trees on your site. Here are all the Quercus trees on your site. Here are all the Betula trees on your site. So what I did there, because this is, I'm totally just kind of discovering things as I go along right now. One of the fun things about Grasshopper, there's always a lot to learn. What I did there was I went to Instance Manager, I went to attribute build, so construct an attribute object. I plugged the attribute build into the attribute input of the insert block by box component, making sure my place Boolean toggle is to false right now. And then I went to my list of tree genuses, so the call pattern, so the 225 values, and I plugged into the layer. So what that means is that each of these, and I guess it automatically makes the layer, each of these trees, they're called here, so each of these 225 blocks, each of the 225 points, etc., will be baked on its corresponding layer. So if you press true like that, it's kind of neat. It bakes it on its layer, like so. So now, again, if you select Prunus, it'll select all the Prunus trees. It's kind of interesting, too, because these blocks, they still function like any block. So, for instance, let's say I did this weird stretch like that. You can see that it's going to do the weird stretch to all of the blocks. So it allows you to essentially quickly replace and edit those blocks. So I'm going to review some of these questions here. So what is the input for A in division? Oh, yeah. So in division, and I'll just set my screen to sort of be the final image here. Division, what it's doing, if we go to the, so the scaling trees to proper height, essentially what we're doing is we have all these block heights, right? So we've moved these blocks that have a height of 10 by default. And what we're doing is we're dividing the height of the block or the height of the tree by the height of the block. So division A is going to be the call pattern list that's coming out of the tree heights. So exactly what Nicholas was saying there. So all of these are the heights of the trees corresponding to these points. B, just a review, is the subtraction that's coming from the domain end minus start, aka the height of each of those unscaled blocks. So does anyone have any more questions about working with blocks and then using them to sort of array trees around the Grasshopper or around the Rhino model. I'm going to see if I can zoom in here so you can see the full definition for your review. Maybe what I'll do is I'll take a high definition shot of this definition, and then I'll just save it to the Dropbox, because I know whenever I have a hiccup in describing a definition, namely in this, that replacing text for replacing members, and it kind of threw me off for a few moments, it might get a little bit confusing, so I'll definitely save a high definition image. But does anyone else have any questions about this or even assignment 1? Yeah, we're not going to be able to see it all. Okay, well, thank you for kind of staying overtime. Like I said, I'll save a high definition image of this tree, I guess a rare definition. And I'll put that in the Dropbox right away. I'll upload this video right away as well. And I will see you all this coming up Wednesday. So just a reminder, assignment 1 is due this coming up Wednesday. This coming up Wednesday, we'll assign assignment 2. So that'll be fun. We'll move forward with that. Okay, thank you.